Welcome to Aurelius Explainer. Tonight, somewhere off the coast of Greenland, in water you will never see, under a sky going dark over the cold edge of the North Atlantic, a single drop of water is about to sink. Not fall, not splash. Sink. Slip quietly beneath the water all around it, the way a stone settles through still air, only slower, much slower, and begin a journey downward into a darkness it will not leave for a very long time. That drop, that one ordinary mouthful of seawater, will not touch the sky again for roughly 1,000 years. Let that settle for a moment. 1,000 years. The drop sinking tonight last felt the open air, last felt wind and light on its surface, this very evening. And the next time it rises, the next time it breaks back into daylight somewhere far across the world, 10 centuries will have passed up here. Empires will have come and gone. The people who will greet it at the surface have not yet been born, and neither have their grandparents nor theirs. The drop does not know any of this. It only knows that it has grown cold and that it has grown heavy, and that the water beneath it can no longer hold it up. And so it goes down. This is the story of that drop. Where it goes. Why it goes there. What carries it, what it carries, and where, after its long, slow circle of the entire planet, it finally comes home. It is the story of the largest river on Earth, a river that runs through every ocean, a river with no banks and no engine, moving silently in the dark beneath the waves while we sleep above it. And like every truly great journey, the strange thing about it is this. Nobody can quite tell you where it begins. You would think that would be a simple question. Where does the ocean's global current begin, and where does it end? It is, after all, the question we came here to answer. But the more closely you look at it, the more it slips away from you. Because this is not a river that runs from a spring in the mountains down to the sea. It is a loop, a closed ring that wraps the whole planet, water sinking in one place, creeping along the bottom for centuries, rising again on the far side of the world, drifting back across the surface and sinking once more, around and around, with no true head and no true mouth. Ask where it begins, and the honest answer is that asking where a circle begins is its own kind of riddle. It begins wherever you choose to stand and watch it pass. Tonight we are choosing to stand off Greenland in the cold at the moment one drop goes under, but you could stand anywhere along the ring and it would be just as true to say it starts there. The current has no source, it only has a shape, and the shape is a circle that takes 1,000 years to close. Before we go down with it, before we follow the drop into the dark, let me ask you something gently, the way you might ask a friend lying near you in the quiet. Where in the world are you listening from tonight? What stretch of coast or what landlocked town, what window with the rain against it, what bed in what city? If you feel like telling me, the comments are there, and I do read them. I like knowing the map of where these slow stories are heard. And if you are new here, if you have only just found this voice in the dark, you are welcome to stay. There is no rush. Subscribe if you would like more nights like this one. More long, calm journeys to drift off inside. There will be no loud moments tonight. Nothing is going to startle you awake. This is a slow descent, on purpose, all the way down to the bottom of the world and slowly back up again, and you are allowed to fall asleep anywhere along the way. The drop will keep going whether you are awake to follow it or not. That is rather the point of it. So loosen your shoulders, let the pillow take the weight of your head, and let us go down together into the cold. Now, the first thing to understand, the thing that surprises almost everyone, is that there is no machinery here. None. When we say the largest river on Earth, you might picture some vast hidden pump some engine churning away in the deep, driving all that water around the globe. There is nothing of the kind, no turbines, no mechanism, no moving parts at all. The entire global circulation, this 1,000-year wheel of water turning beneath every ocean, is driven by nothing more than two simple things deciding what should sink and what should float. Temperature and salt, that is all, cold and salt. The whole grand machine runs on those two quiet facts and on the oldest force there is, which is gravity, doing what it always does, pulling the heavier thing downward. Here is how those two facts work, and they are gentle enough to follow half asleep. Think of a glass of water on a shelf. Whether that water sinks or rises, whether it sits on top of its neighbors or slides beneath them, comes down to one thing: density. How much weight is packed into each handful of it? Heavier water sinks, lighter water floats up over the top. And out in the sea, two things set that density, two dials that turn it up or down. The first dial is temperature. Cold water is denser than warm water, heavier. This is the opposite of what we feel in air, where warm air rises, but in the sea, cold is the heavy thing. Warm water is loose and light and spreads out across the top. Chill it down and it tightens, it draws in on itself, it gets heavier, and it wants to go down. You can almost feel it if you imagine it. Warm water is a sleeper sprawled out across the whole bed. Cold water curls up small and tight and slides to the bottom. So that is the first dial. The colder the water, the heavier it gets, the more it wants to sink. The second dial is salt. The sea is salty, as everyone knows, but the amount of salt is not the same everywhere, and that matters more than you might think. Saltier water is denser than fresher water, heavier. Dissolve more salt into a handful of seawater, and you have packed more weight into it, and down it goes beneath the fresher, lighter water around it. If you have ever floated more easily in the sea than in a swimming pool, you have felt this. The salt holds you up because the salty water is heavier than you are. The same heaviness that lifts your body is the heaviness that, out in the deep, pulls one parcel of water down beneath another. And how much salt are we talking about? Just as a quiet aside, the kind of number you can let drift past you, the average seawater carries about 35 grams of dissolved salt in every kilogram of water, 35 parts in 1,000. A small amount, really, when you say it like that, a few spoonfuls in a large jug. But here is the delicate, beautiful thing. The differences that decide the fate of all that water are smaller still. Not whole units of salt, but fractions of a unit. A little saltier here, a little fresher there, a degree or two colder in one place than another, and that is enough. That tiny imbalance, a sliver of salt, a breath of cold, is all it takes to tip a vast body of water from floating to sinking. The whole global river turns on differences almost too small to taste. So picture the two dials together now, temperature and salt, thermo for heat and haline for salt. Put those two old words together and you get the proper name for this whole system, the thermohaline circulation. That is the formal name, thermohaline, heat and salt, the two things that set the density that drives the loop. Scientists also call it, more broadly, the meridional overturning circulation, the great overturning of the seas from the surface to the deep and back. And the part of it that runs through the Atlantic, the part we will be following most closely tonight, is called the Atlantic meridional overturning circulation. Those are mouthfuls, I know, and you do not need to hold on to them. But there is one name for all of this that is easier to keep, a name a single scientist gave it that has stuck ever since. The Great Ocean Conveyor Belt. An oceanographer named Wallace Smith Broecker popularized that phrase, the Great Ocean Conveyor Belt, back in the late 1980s, and it caught on because it paints the picture so well. A belt, a loop running endlessly around, carrying its cargo from one end of the world to the other and back again. We will come back to Broecker later and to others who first traced this hidden river. For now, just hold the picture. A belt of water turning slowly, run by nothing but cold and salt. And because cold and salt are the only two things that matter, the deep ocean ends up arranged in a way that is almost tidy, almost architectural. Different bodies of water, each made cold and salty in its own particular place, each carrying its own exact blend of temperature and saltiness, do not simply blur together into one grey soup. They stack. The very heaviest water, the coldest and saltiest of all, sinks to the absolute bottom and stays there. Water that is heavy but a little less so settles in a layer above it. Lighter water rests above that and so on up toward the surface, layer upon layer, each one keeping its own character, like the pages of a book pressed together but still separate, each page its own. Every layer carries a kind of signature, written in its exact temperature and its exact saltiness, and that signature is so distinct that scientists can recognize a particular body of water thousands of kilometers from where it was born, the way you might know a friend's handwriting from across a room. The deep sea is not chaos. It is stacked and layered and ordered by nothing but those same two dials, cold and salt, sorting everything by weight in the dark. Now we are ready to go back to our drop, the one sinking off Greenland tonight, and to ask the question that really matters. Why there? Why does the sinking happen in that particular cold corner of the North Atlantic, and not just anywhere? To answer that, we have to follow the water that arrives there and trace where it came from, because the drop that sinks tonight did not begin its life cold. It began warm, tropically warm. It began its journey toward Greenland thousands of kilometers to the south in sunlit, balmy water, and it was carried all that long way north by a current you have certainly heard of, the Gulf Stream. The Gulf Stream is one of the great rivers of the surface ocean, a warm and powerful flow of water that sweeps up out of the tropics, up along the eastern edge of North America, and then strikes out across the Atlantic toward Europe, where it becomes known as the North Atlantic Current. Picture it as a vast warm conveyor at the surface, a moving ribbon of mild tropical water, kilometers wide and running fast, carrying the heat of the equator northward toward the cold top of the world. Our drop is somewhere in that ribbon, being borne steadily north, still warm, still light, still floating easily on the surface where the air can touch it. But two things are happening to that warm water as it travels north, and both of them are slowly, quietly sealing its fate. The first is that all along its journey under the sun, the surface water is evaporating. Some of it lifts off into the air as vapor, rising away, leaving its salt behind. And when water leaves but salt stays, what remains gets saltier. So mile by mile as the Gulf Stream carries our drop north, the water is concentrating, growing saltier than it was, dialing up that first dial of density without anyone noticing. By the time it reaches the far north, this is some of the saltiest surface water in the world ocean. Hold on to that. The Atlantic, especially up here, is salty. That matters more than almost anything else in this whole story, and we will return to exactly why before long. The second thing happens at the end of the road when the warm, salty water finally arrives in the cold seas off the top of the world. Up there, around Greenland and Iceland, across the seas the sailors of old called the Nordic Seas, the Greenland Sea and the Iceland Sea and the Norwegian Sea, and over in the Labrador Sea on the other side of Greenland, the air is bitterly, brutally cold, polar cold, and when warm water meets cold air, the water gives up its heat. It has to. All that tropical warmth the Gulf Stream carried so faithfully north, all those kilometers, is released here, lifted away into the freezing polar sky. This is no small thing, that release of heat. It is, in fact, one of the great gifts this whole system gives to the world above it, and we will spend real time later on where all that warmth goes and what it does for the people who live in its path. But for the drop, for the water itself, the loss of heat is the beginning of the end of its life at the surface. Because now, watch what happens. The water arriving here was already salty, made salty by all that evaporation on the long trip north. That is the second dial turned high, and now, meeting the polar air, it is losing its heat, getting colder and colder, which turns up the first dial too. Salty and getting cold, cold and staying salty, both dials of density climbing at once. The water grows heavier and heavier, packing more weight into every handful, until at last it crosses a threshold. It becomes denser than all the water beneath it. And once that happens, there is nothing to hold it up anymore. The sea can no longer support its own weight, and so it sinks. This is the moment we began with. This is the drop going under off Greenland tonight. It is not being pushed. Nothing shoves it. It simply becomes too heavy to float, and gravity, patient and certain, takes it down, down through the water that is lighter than itself, down past the depth where the light gives out, down to 2,000 meters, 3,000, as far as 4,000 meters below the surface, into the cold black middle of the ocean. The water that sinks here has a name, the way the great layers all have names. This is North Atlantic deep water, born in the cold seas off Greenland and Iceland and Labrador, formed from warm tropical water that travelled all this way, only to lose its heat and grow heavy and fall. North Atlantic deep water. Remember it. We will be travelling with it for a long time and a long way. And once it has reached its depth, this newly sunk water does not simply sit still. It begins, slowly, to move. It turns and starts to flow south, away from the pole, sliding along the deep floor of the Atlantic, a hidden river running in the dark beneath the warm surface currents going the other way. Above, near the top, the Gulf Stream still races north, warm and bright. Below, unseen, our drop is now part of a deep southbound flow, creeping the other way, back toward the equator and beyond, the return half of the Great Belt beginning to turn. The conveyor has taken on its cargo, the wheel has begun to roll. But I have left a thread hanging, and you may have already felt the tug of it. I said this sinking happens in the North Atlantic, off Greenland, in the Nordic Seas and the Labrador Sea. I have been very specific about that. And you might reasonably ask, well, why there? The North Pacific is cold too, up at the top, off Alaska and the Bering Sea, just as far north, just as frigid. Why doesn't the Great Conveyor sink there as well? Why does this enormous engine of the deep ocean have its beginning in the Atlantic, and not, or at least not nearly so much, in the Pacific, on the other side of the continent? The cold is in both places, the polar air is in both places, so why the Atlantic? So, why? Here is the part that catches almost everyone by surprise, the first real twist in our quiet story, and I will plant it now and let it work on you in the dark. The reason the water sinks in the Atlantic and not in the Pacific is not the cold. It is not, in the end, about temperature at all. Both oceans have the cold, the thing the Atlantic has that the Pacific does not, the secret ingredient that decides where the great river of the deep begins, is salt. There is one reason this conveyor sinks in the Atlantic and not the Pacific, and the cold is not it. Keep that with you as you drift. It isn't the cold. So tonight, we have stood at the place where one ordinary drop, having ridden the Gulf Stream all the way from the tropics, having grown salty under the sun and cold under the polar sky, became too heavy for the sea to hold and slipped quietly beneath the waves off Greenland, on its way to a darkness it will not leave for 1,000 years. We have learned that the great conveyor belt runs on no engine at all, only the two soft dials of temperature and salt, cold being heavy and salt being heavy, gravity pulling the heaviest water down into a stacked and layered deep. And we have watched the very first step of the journey, the birth of North Atlantic deep water in the cold seas off Greenland and Iceland and Labrador, sinking thousands of meters into the black and turning south to begin its long creep around the world. The drop is under now. It is below the light. It is colder than it has ever been and heavier, and it is moving slowly into the deep. Ahead of it lies the strangest part of the question we came to answer, the secret of the salt, and a place at the bottom of the world where the coldest, saltiest, heaviest water on the whole planet is made, not by cooling, but by freezing. But before we follow it down, before we let the salt give up its secret, it is worth lingering here a moment longer at the surface where the whole thing quietly begins. Because nobody can truly tell you where the great current starts. That sounds like a strange thing to say of a river so vast it touches every ocean on Earth, but it is the honest answer. A river on land has a source, a spring on a hillside, a place you can stand and say, "Here, this is where it is born." The great ocean conveyor has no such place. It is a loop. It closes on itself. The water sinking off Greenland tonight is the same water that rose somewhere far away 1,000 years ago in the light and was carried back north along the surface to this exact spot to grow heavy and sink again. So when we ask where it begins, the deep ocean only offers us a circle, turning slowly, with no first link in the chain. The drop you are following is not at the start of anything. It is part way around a wheel that has been turning since long before there were people to wonder about it. And wherever you are tonight, lying in the dark with this turning over in your mind, I would like to know where in the world you are listening from. Leave it in the comments if you feel like it. A city, a country, a coast. It is a small thing, but it makes this vast and lonely subject feel a little less lonely, knowing the same slow story is unspooling in so many rooms at once. And if you are new here, you might press subscribe softly, so the next quiet journey can find you. There is no hurry. We are going to be a long time in the deep tonight, and there is nowhere we need to be. So let us go back to the elegance of the thing, because it really is elegant, and it is the kind of idea that is restful to hold. There is no pump. I keep returning to that because it is the part most people never quite believe at first. When you imagine a current that wraps the entire planet, that carries warmth toward Europe and pulls carbon down into the abyss and stirs every ocean basin into one connected body of water, you imagine, naturally, some great machinery driving it, some engine, some force pushing the water along. And there is none. There is only weight. There is only the simple fact that some water is heavier than other water, and heavy things sink, and that is the whole of it. Two things decide how heavy a parcel of seawater is. The first is temperature. Cold water is denser than warm water, packed a little tighter, and so the cold sinks beneath the warm. You have felt a version of this yourself in a lake in summer, when you swim down and your foot finds the cold layer waiting below the warm skin of the surface. The ocean does the same thing, everywhere, all the time. The second is salt. Saltier water is denser than fresher water, heavier for the dissolved salt it carries. The sea, on average, holds about 35 grams of salt in every kilogram of water, a number worth saying once and then letting drift away. But the average is not what matters. What matters are the small differences, a fraction more salt here, a couple of degrees colder there, and a parcel of water that was floating becomes a parcel of water that sinks. That is the entire trigger. Temperature and salt, the two soft dials, and gravity reading them and deciding, quietly, what stays up and what goes down. And because those two properties travel with the water, because a parcel that was made cold and salty in one place carries that coldness and saltiness with it for a very long time, the deep ocean ends up sorted, layered, stacked by density like the pages of a closed book. Scientists can lower an instrument thousands of meters down, thousands of kilometers from anywhere this water was last at the surface, and read its temperature and its salt and know from those two numbers alone where it was born. The water remembers. It keeps the signature of the sky it last touched and the sea that made it heavy, written into its cold and its salt, and it carries that signature with it all the way around the world. This is what the scientists mean when they speak of water masses, distinct bodies of deep water, each with its own temperature and salinity signature, riding one above another in the dark. The deep is not a single, undifferentiated cold. It is an architecture. Now let us follow the heaviest water of the north as it is made, because this is the first sinking, the one our drop has just joined. Far to the south, in the warm tropics of the Atlantic, the sun beats down on the surface of the sea, and two things happen to the water there. It grows warm, of course, but it also grows salty because the heat evaporates water off the top, lifting it into the air as vapor and leaving the salt behind in what remains. So the tropical Atlantic becomes warm and salty, a thin, bright layer riding over the cold below. And this warm, salty water does not stay in the tropics. It is gathered up and carried north. The carrier is the Gulf Stream, and beyond it, reaching farther into the high latitudes, the North Atlantic Current. This is the surface limb of the conveyor, the part that moves quickly, on the order of meters every second, a genuine river in the sea, racing up the eastern edge of North America and then bending out across the open Atlantic toward Europe. It carries the warm, salty water of the tropics north and farther north into the cold toward the pole, and as it goes, something is taken from it. What is taken is the heat. Out over the Nordic Seas, the cold seas off Greenland and Iceland and Norway, and over the Labrador Sea to the west, the warm water meets the frigid polar air. And the warmth which the water carried all the way from the tropics is given up to that air. It leaves the sea and enters the atmosphere, where it warms the high north and downwind the lands of northwest Europe. That heat does not vanish. It is handed over. The water arrives warm and leaves cold, and the warmth it surrenders is one of the quiet reasons the far north is more livable than it has any right to be, though that is a story with a careful correction in it that we will come to. But think about what is left behind in the water once the heat is gone. The warmth that kept it light has been given away. What remains is water that is now cold, deeply cold, having lost its heat to the polar air. And it is still salty because the salt it gathered under the tropical sun never left it. The vapor rose and the heat departed, but the salt stayed. So here, in these cold northern seas, is a parcel of water that is both cold and salty at once, heavy from the cold, heavy from the salt, heavy twice over, and now heavier than anything beneath it. And so it sinks. Not violently, not in a rush, but quietly, the way everything in this story happens quietly. The cold, salty surface water of the Nordic Seas and the Labrador Sea grows dense enough to slip beneath the water around it and descend down through the dark 2,000 meters, 3,000, 4,000, until it settles into the deep Atlantic. This is the birth of North Atlantic deep water, the first great mass our drop has joined, formed in just these few small cold seas of the high north, and from there spreading out to fill the abyss. And once it is down there, it does not simply sit, it begins to flow, It turns south, hugging the western edge of the Atlantic basin, and starts the long, slow journey back toward the equator and beyond, a deep current running invisibly beneath the bright surface river that is still racing north overhead. This is the loop closing on itself, the warm going north at the top and the cold returning south at the bottom, the two limbs of a single turning wheel. It is this turning that the oceanographer Wallace Broecker in the late 1980s gave the name that stuck, the Great Ocean Conveyor Belt, a picture simple enough to hold in the mind and large enough to wrap the planet. The more technical names are quieter and more exact. Thermohaline circulation from the heat and the salt that drive it. The meridional overturning circulation, the great overturning of water from surface to deep and back. And of that overturning, the most studied limb, the one running up and down the Atlantic that our drop has just entered, the Atlantic meridional overturning circulation, the AMOC, the part the scientists watch most closely of all. And here is the thing to carry down into the dark with you, the loop we opened and have not yet closed. The water sinks here in the Atlantic. It does not sink in the Pacific. The Pacific has cold seas in its north too, just as cold, just as capable of chilling the water at the surface. And yet there is no great sinking there, no Pacific equivalent of this northern descent, no North Pacific deep water borne off its northern shores the way it is borne off Greenland. Both oceans have the cold. Only one of them makes the heavy water that begins the conveyor. And the reason, as I told you, and will keep telling you until we reach it, is not the cold at all. The reason is the salt. The Atlantic and the Pacific are not equal in their saltiness, and that inequality, that small, quiet difference measured in fractions of a gram in every kilogram of water, is what decides where the conveyor begins. The Atlantic is, on average, saltier than the Pacific. Not dramatically so, not in a way you would taste if you swam in both, but enough that when the cold polar air does its work in the north, the Atlantic water crosses a threshold the Pacific water cannot reach. The Atlantic water, already carrying more salt, already sitting closer to the density needed for sinking, needs only the cold to push it over. The Pacific water, fresher by those same quiet fractions, feels the same cold and still does not sink. It chills, it slows, but it does not plunge. The question then is why the Atlantic should be saltier at all. They are both ocean, they are both fed by the same rivers and the same rains and the same evaporation. They sit under the same sky, and yet the salt is not evenly distributed between them. And the reason for that is a piece of geography so ordinary, it seems unworthy of an explanation this large. Between North America and South America, the two great pieces of the American continent nearly touch, and across the narrow land of Central America, the trade winds blow steadily from east to west. Those winds carry water vapor. They pull moisture from the Atlantic surface through evaporation, and they carry it westward across the land bridge, and eventually that moisture falls as rain over the Pacific. The Atlantic loses water to the sky, the Pacific gains it back, and what the Atlantic loses is the fresh water, the pure salt-free fraction, because evaporation takes only water molecules, never the dissolved salt, which stays behind. Every time a small cloud forms over the tropical Atlantic and drifts westward over Panama, over Costa Rica, over Nicaragua, the Atlantic becomes very slightly saltier than it was before. Not in a way you could measure on any single afternoon, but over thousands and millions of years, this gentle, steady theft of fresh water has made the Atlantic the saltier basin, and the saltier basin is the one whose cold northern waters can grow dense enough to sink. A difference of rain patterns over a thin strip of land between two continents is part of the reason a drop of water off Greenland tonight will spend 1,000 years in the dark. The world is connected at scales that seem impossible until you follow the logic all the way down. And so the Pacific sits there in its northern reaches, vast and cold and fresh, capable of chilling its surface water in winter just as the Nordic Seas do, and the water slows and the currents shift, but no great column of water tips over the edge and descends. The North Pacific is too fresh. It does not make the deep water that would fill the abyss beneath it. The abyssal Pacific is not empty, it is filled, slowly and patiently, by water that arrives from elsewhere, water born in other places and carried to the Pacific along the bottom after journeys of centuries. The Pacific's depth is occupied by water that the Pacific itself never made, water that came from far away, born in places where the conditions for sinking are met, and those places are few. This is one of the things about the ocean that is genuinely surprising when you hold it clearly in your mind. The vast global abyss, the dark interior of this planet-spanning body of water, is fed from a small number of nurseries. Not many. Not dozens of places spread evenly around the high latitudes of both hemispheres. A handful. Compact, specific geographical zones near the poles, where the conditions of cold and salt and wind and current conspire together to push surface water down into the deep. Everything below the warm, sunlit skin of the ocean, and that deep, cold interior, is the great majority of the ocean's volume, the vast bulk of it, was born in one of these few small places or was formed from water that arrived there by mixing over time. Think of it this way. Imagine a library enormous, every floor stacked with books going back centuries, each shelf full. And feeding that entire library are just 2 or 3 small printing presses running quietly in obscure corners, not factories, not great industrial halls, small specific machines turning out the pages that fill the shelves of the deep. The North Atlantic's Nordic Seas and Labrador Sea are one such press, and around Antarctica, in the seas at the far south of the world, there is another. And it is here that the densest water on Earth is made, the water that sinks to the very bottom of everything. To reach it, follow the drop we have been watching. It has sunk from the surface of the Nordic Seas, grown cold and dense enough from the heat it gave away to the polar air, and it has descended to depths of 2,000, 3,000, 4,000 meters in the North Atlantic. Now it moves southward along the bottom, joining what is called North Atlantic Deep Water, the NADW, a distinct and identifiable layer of the ocean carrying the chemical signature of where it was born. Its temperature, its salinity, the oxygen it last breathed at the surface before it went under. It moves slowly. We will come back to how slowly. For now, follow it south, toward Antarctica, toward the other nursery, the older and colder one, where something is happening on the surface of the sea that makes what we saw in the North Atlantic look almost gentle. It is winter in the Southern Ocean. The Antarctic winter is not a season in the way the word suggests in other latitudes. It is a long darkness, a compression of cold and wind and ice that extends over months and turns the surface of the sea around the continent into something rigid. Sea ice grows outward from Antarctica, spreading north across the Southern Ocean, covering millions of square kilometers of what was open water. And in the forming of that ice, something happens that is the pivot of the whole story. Something that looks simple but carries consequences that reach to the very bottom of the world. Sea ice is not salty. This is the crucial thing. When seawater freezes, the ice that forms is made almost entirely of pure water. The salt does not fit neatly into the crystal structure of ice. It is rejected, expelled, pushed out of the forming crystals and back into the liquid water just beneath. The ice grows upward and outward, a clean white layer of nearly fresh water thickening on the surface, and below it, rejected and concentrated, the salt accumulates, This process has a name: brine rejection. And it is one of the most important things the sea ice does, not for the ecosystems that shelter within it or beneath it, though there are those, but for the physics of the water below. When the salt is expelled into the water beneath the growing ice, that water becomes colder and saltier at the same time. Cold because the Antarctic winter is drawing heat from it continuously. Salty because the forming ice has just handed back all the dissolved salt it could not take with it into the crystal. And cold and salty together mean dense, very dense, the densest water in the open ocean. The water that forms beneath the sea ice around Antarctica, in particular in the Weddell Sea on the Atlantic side of the continent, and in the Ross Sea on the Pacific side, is the heaviest water the ocean makes. It is called Antarctic Bottom Water, the AABW, and when it forms, there is nothing beneath it to stop it. It sinks, it does not drift or settle gradually, it pours, it moves down the Antarctic continental slope, the underwater cliff at the edge of the continent, dropping toward the abyss, and because it is denser than anything already down there, it goes all the way to the bottom, the very bottom. It fills the deepest basins of the global ocean, spreading outward from Antarctica along the seafloor, moving north under the deep waters of the Atlantic and Pacific and Indian Oceans, occupying the absolute lowest layer of the world beneath the waves. Antarctic bottom water is the basement. Everything else is built on top of it, and above it, riding in the next layer up, separated not by a wall but by a gradient of density, is the North Atlantic deep water, the water our drop was born into off Greenland. The two great deep water masses are stacked: Antarctic bottom water at the floor, North Atlantic deep water in the layer above, each identifiable by its signature of temperature and salinity, detectable thousands of kilometers from where it formed, like a postcard from its birthplace carried by the water itself through the dark. Scientists can take a water sample from the middle of the Pacific and identify, from its temperature and salt content and oxygen levels, whether it came from the North Atlantic or from around Antarctica, and roughly when it sank. The water remembers where it has been. The deep ocean is layered in this way not because of anything that acts upon it from outside, but because of the simple physics of density. Denser water settles below less dense water, just as oil floats above water in a glass. Just as cream rises and grounds settle, the ocean sorts itself by weight, and the result is a stratified architecture, distinct water masses sitting in their appointed places according to how heavy they are, each layer reflecting the conditions of the distant place and season that made it. The cold numbers attached to this are worth sitting with for a moment. The deep ocean, the vast interior below the sunlit surface, sits at temperatures between roughly 0 and 4 degrees Celsius, almost everywhere in the world. Not the water at the surface, which varies enormously with latitude and season, the deep water, the interior, the majority of the ocean's volume. 4 degrees is close to the temperature of a refrigerator. 0 degrees is the freezing point of pure water. The Antarctic bottom water near its origin can be below 0 Celsius, kept liquid only by the salt dissolved in it, which lowers the freezing point, and by the pressure of the water above, which lowers it further still. At the very bottom of the Weddell Sea, in the coldest deep water on Earth, the temperature can reach -1.8 or -2 degrees Celsius, and the water remains liquid, moving slowly, impossibly cold by any ordinary standard, but too salty and too pressurized to turn to ice. This is the world the drop has entered, a world of near-freezing darkness, of water so cold that metabolism at the surface of the sea would shut down entirely, of pressures that would crush any air-filled vessel, and it is vast. The warm, sunlit ocean that we see in photographs, the turquoise shallows and the blue sparkle of the open sea under sun. That world extends only to a depth of roughly 200 meters before light runs out. 200 meters is the bottom of what oceanographers call the photic zone, the zone where light still reaches in quantities sufficient for photosynthesis. Below 200 meters, the light fails. By 300 meters, it is essentially gone. Below that, there is no sun, no blue, no green, no photosynthesis. Only darkness, temperature, and time. The warm, sunlit layer, when you set it against the total depth of the ocean, an average of around 3,700 meters, is a skin. A thin, bright, living skin stretched over a dark and cold and ancient interior. The conveyor's deep limb, the returning flow that carries NADW and AABWR through the abyssal world, runs through that darkness entirely. It never surfaces. It does not touch the light. It moves through a world where there is nothing to see, nothing to illuminate the path, nothing but the slow drift of cold water along the contours of the sea floor. There is one more thing that shapes the path the deep current takes as it moves through this dark world, and it is worth understanding because it explains something that might otherwise seem arbitrary. Why the deep water flows the way it does, and why the boundary currents that carry it tend to hug one side of an ocean basin rather than spreading evenly across the floor. The thing is called the Coriolis effect, and it is a consequence of the fact that the Earth is rotating. The Coriolis effect does not push or pull anything directly. It is not a force in the ordinary sense of something striking an object and moving it. It is more subtle than that. It is the effect of being on a rotating sphere. When anything moves freely across the surface of a planet that is turning beneath it, water, air, a fired cannonball, it appears to curve. In the northern hemisphere, moving objects curve to the right. In the southern hemisphere, to the left. The water does not know this is happening. The water is following its own momentum, moving in a straight line relative to itself, but the Earth has turned slightly beneath it, and from the Earth's point of view, the path of the water has bent. For the deep currents, the Coriolis effect means that as North Atlantic deep water flows southward along the floor of the Atlantic, it is deflected to the right, which in the southward moving frame means toward the western side of the ocean. The deep water is pushed against the western boundary of the Atlantic basin, the underwater slopes on the American side, and it flows southward, hugging that wall. This flow has a name, the deep western boundary current. It is not the kind of current you could see or feel. It is a slow movement of cold, dense water along the base of a continental slope, in the dark, at depths of 2 to 4 kilometers, moving at centimeters per second. But it is real. It is continuous, and it is how the deep water born in the North Atlantic makes its long southward journey. And slow is the right word for it. This is perhaps the hardest thing to feel after months of surface currents and ocean charts and satellite images that show the Gulf Stream racing north, brilliant orange and red on the satellite maps, moving at 1 or 2 or sometimes more than 2 meters per second, a real river moving fast enough that a person dropped into it would be pulled away at the pace of a brisk sprint. The deep return flow is nothing like that. The abyssal current creeps. It moves at centimeters per second, sometimes less. A few centimeters per second is slower than a person walks, slower than a person shuffles across a room, slower than almost anything we would recognize as motion. A parcel of water in the deep western boundary current might move a kilometer in a day or less. The Gulf Stream covers the same distance in minutes. The surface of the ocean and its interior are not merely different in temperature or light, they are different in pace. The surface is fast, the deep is geological in its slowness, and it is that slowness added to the vast distances the deep water must travel. From the North Atlantic down to the Southern Ocean, and then distributed through the Indian and Pacific Oceans, that produces the number that is perhaps the most remarkable single fact about the conveyor. One circuit of a single parcel of water from the moment it sinks off Greenland or from the ice shelves of Antarctica to the moment it finally rises back toward the surface and breathes air again takes on the order of 1,000 years. Some estimates extend the figure to 2,000 years, depending on the path taken and the portion of the circuit under consideration. The number varies. The ocean is not a clock, but the order of magnitude is consistent. Not a year, not a decade, not a century, but a millennium. The water moving slowly along the floor of the Atlantic right now in this darkness was last at the surface of the ocean roughly 1,000 years ago. At the surface 1,000 years ago, the world was different in ways that are difficult to fully picture. The medieval warm period was underway in Europe. Viking settlers were establishing themselves in Greenland. Leif Erikson and his crew were somewhere on the coasts of North America. The Sung dynasty in China was printing paper money for the first time. The great cathedral at Chartres had not yet been built. And somewhere in the Nordic Seas or off the Antarctic coast, a parcel of water at the surface released its last breath of air, grew cold and dense and heavy, and slipped beneath the surface of the sea. It has not seen the sky since. It has moved slowly southward through the dark for 1,000 years, and it has not yet completed its circuit. The deep water carries a record of this long absence. It carries it in its oxygen content. At the surface, the water equilibrates with the atmosphere, absorbing oxygen that will later support life in the deep. When the water sinks, it takes that oxygen with it. Over time, in the deep, tiny organisms, bacteria, the faint remnant of a biosphere sustained on what drifts down from above, consume the oxygen slowly. The older the water, the longer it has been away from the surface, the more of its original oxygen has been consumed. Scientists can take a sample of deep water and measure its oxygen content and get an estimate, imperfect and approximate, of how long that water has been away from the air. The oldest deep water in the world is found in parts of the North Pacific. Water that has not touched the atmosphere in roughly a millennium, that set out on its journey perhaps before Chartres was built and has been moving slowly in the dark ever since. There is something in that fact that is difficult to absorb and easy to let settle into the body in a quiet way. Not an anxious thing, a large and calming thing. The ocean is old and dark and patient in its movements, and it holds within itself a record of the world's past that is written not in stone, but in cold and salt and oxygen, in the slow chemical diary of water that has been away from the sky for longer than most human civilizations have existed. And while the deep water has been making this millennial journey along the bottom, something has been falling past it. Something that has been falling past it continuously without pause, since long before the water sank, something so slow and so quiet that it goes unnoticed until you have the right kind of light to see it, and then it is like looking at a snowfall in a room where you forgot it had been snowing all along. It snows in the deep ocean, not water snow, not ice crystals falling from clouds, but a snow of tiny particles, organic and inorganic, drifting perpetually downward from the sunlit layer above. Scientists, when they first sent cameras and lights into the deep ocean and watched the water, saw it. A continuous fall of small white particles drifting in slow motion in every direction the light touched. They called it marine snow. The name is accurate and it is beautiful, and it does not capture entirely what is moving in that snow, what each small particle represents, or what the cumulative fall of all those particles over all the oceans of the world means for the planet above. The snow begins at the surface, in the photic zone, in the thin, bright layer where the sun reaches. There, in quantities that would be invisible to the naked eye from any distance, float the phytoplankton, microscopic marine plants, single-celled organisms some barely a few micrometers across, carrying chlorophyll in their bodies, using the energy of sunlight to pull carbon dioxide from the water around them and convert it into organic carbon, the carbon of living things. They are not glamorous, they are not visible, you cannot see a phytoplankton, but they are the base of nearly all marine food webs, the foundation of the ocean's living world, and they are performing photosynthesis on a scale that together accounts for roughly half of all the photosynthesis that happens on Earth, as much in total as all the land plants and forests and grasses combined. And they die, they are eaten, and their predators are eaten, and at every level waste is produced, and everything that is produced is subject to gravity. A phytoplankton cell dies and begins to sink. An organism eats a phytoplankton and excretes what it cannot use, and that excretion, a fecal pellet dense and small, begins to sink. Larger organisms produce larger particles, and those sink faster. Everything that lives in the sunlit ocean and dies or excretes eventually produces something that falls. Not all of it makes it to the deep. Much of it is consumed again by other organisms on the way down or dissolves back into the water. But some fraction of it, a real and significant fraction, makes it through. It drifts past the 200-meter boundary where light fades. It drifts past 1,000 meters, 2,000, 3,000, entering the abyssal zones where nothing photosynthesizes and very little lives except on what arrives from above, and it settles eventually on the floor. This is the biological pump. The phrase is not poetic, but the process it describes is. The biological pump is the mechanism by which the living surface of the ocean takes carbon from the air, carbon dioxide dissolved into the surface water from the atmosphere, converts it into organic matter through photosynthesis, and then allows a portion of that organic matter to sink into the deep ocean, where it is removed from contact with the atmosphere for as long as the water it sinks into stays away from the surface. And that, as we have been noting, can be a very long time. The numbers behind this process are difficult to hold in the mind, but worth pausing over. Estimates of how much carbon the biological pump exports downward each year vary depending on method and on where exactly one measures, but the figures commonly cited fall somewhere in the range of 5 to 10 gigatons of carbon annually, and some estimates run higher. A gigaton is 1 billion tons. The pump is not a curiosity at the edge of the ocean story. It is one of the central mechanisms by which this planet regulates the composition of its own atmosphere, and it has been doing so quietly for hundreds of millions of years. Without it, the carbon that the surface ocean perpetually draws down from the air would have nowhere to go. It would return to the atmosphere. The concentration of carbon dioxide above us would be substantially higher than it is. The ocean's interior holds roughly 50 times more carbon than the atmosphere does. 50 times. And the biological pump is a primary reason why that carbon is down there in the dark rather than up here in the air. The ocean is not merely a body of water. It is the planet's largest active carbon reservoir, cycling with the atmosphere on timescales that dwarf anything in human experience. And now we arrive at the question that has been waiting since the beginning of this journey. We know that the deep ocean is cold and dark and slow. We know that it is fed from above by marine snow falling through the photic zone, carrying carbon down. But we have not yet asked the most important question about this cold, dark, vast interior. Why does the water in it sink in the first place, and why does it sink where it does and not somewhere else? The answer begins with salt. There is one reason the global conveyor descends into the deep in the Atlantic and not in the Pacific. And it is not the cold, or not the cold alone. It is the fact that the Atlantic is, on average, saltier than the Pacific. The difference is not enormous in absolute terms, a matter of fractions of a practical salinity unit, fractions of a gram of dissolved salt per kilogram of water. But In the physics of seawater, small differences in salinity compound with small differences in temperature, and together they decide what sinks and what stays at the surface with a precision that has no margin for error. The Atlantic's extra saltiness is not an accident. The trade winds that blow across Central America carry water vapor westward from the Atlantic into the Pacific, a steady, invisible transfer of fresh water out of one basin and into another. Evaporation over the tropical Atlantic removes water and leaves salt behind. The salt accumulates. Over geological time, the Atlantic has become the saltier ocean, and that saltiness is part of what makes it capable of forming the dense, heavy water that sinks into the global abyss. The North Pacific, by contrast, is too fresh. Its surface water is simply not salty enough, even when cold, to become dense enough to sink to great depth. The conveyor sinks in the Atlantic. The Pacific receives the deep water eventually, but it does not generate it at the surface the way the North Atlantic does. This asymmetry, one ocean producing the engine, another receiving its product, is a consequence of the particular arrangement of continents and wind patterns on this specific planet, and it is not guaranteed to be permanent. But the North Atlantic is only one of the nurseries, and it is not the one that produces the densest water of all. For that, we must travel south, very far south, to the edge of the Antarctic continent, where the sea freezes in winter over an enormous area, and where something happens in that freezing that is unlike anything else the ocean does. When seawater freezes, it does not freeze evenly. Ice, forming from water, prefers to incorporate water molecules and to exclude salt. The salt does not fit comfortably into the crystalline structure of ice, and so as the ice forms, it expels the salt back into the water immediately beneath it. This process is called brine rejection, and it is one of the most consequential small-scale processes in the entire ocean system. The water beneath the forming sea ice receives this rejected salt and becomes, in the Antarctic winter, extraordinarily salty, far saltier than normal seawater, and already cold because it sits beneath ice at the frigid surface of the Southern Ocean. Cold and very salty together means very dense, and very dense means it sinks. It does not merely sink, it sinks to the absolute bottom. The water that forms in the Weddell Sea and the Ross Sea by this process of brine rejection is called Antarctic Bottom Water, and it is the densest, coldest named water mass in the global ocean. It flows down the continental slope off Antarctica with a persistence that has been measured and tracked by oceanographers, spreading outward across the floors of the world's ocean basins, finding the lowest points, filling the deepest trenches and the widest abyssal plains with water that last touched the Antarctic air during the winter freeze. Its temperature can be below 0 degrees Celsius, kept liquid not by warmth, but by the pressure of kilometers of water above it, and by its own salinity, which depresses the freezing point just enough to keep it flowing rather than solid. It moves slowly in the way that all deep water moves slowly, but it moves with a certainty born of its own density. Nothing in the ocean is heavier than Antarctic bottom water. It finds the bottom because it must. Above it, layered in the way that fluids of different densities always layer themselves, sits the North Atlantic deep water. The NADW is cold and salty, formed in the Nordic Seas and the Labrador Sea, but it is not quite as cold or as salty as the Antarctic bottom water beneath it. So it sits above. The deep ocean is stratified, arranged in layers by density the way a still lake is arranged in layers by temperature in summer, except that the ocean stratification is far more permanent, far more extensive, and far more consequential. The Antarctic bottom water occupies the absolute floor. The North Atlantic deep water rides above it. Other intermediate water masses fill the levels between. Each layer has a signature, a particular combination of temperature and salinity that marks where it was formed, and that persists for centuries because the deep ocean mixes only very slowly. What does this cold abyss actually feel like as a physical space? The temperature of the deep ocean is remarkably uniform across the world's basins. Below a few hundred meters, away from the surface layer where sunlight and seasons still operate, the water settles into a range of roughly 0 to 4 degrees Celsius. Not everywhere exactly the same, but within that narrow band, almost everywhere. The Antarctic bottom water is at or slightly below zero. The North Atlantic deep water sits in the low single digits. And this cold extends across the vast majority of the ocean's volume, because the vast majority of the ocean's volume is deep. The warm, sunlit, familiar sea that we think of when we think of the ocean, the blue-green, wave-tossed, full of light, is a thin skin over a cold, dark, enormous interior that operates on entirely different principles. Light penetrates meaningfully only to about 200 meters. Below that boundary, the bottom of what oceanographers call the photic zone, there is no photosynthesis, no plant growth, no possibility of converting sunlight into living matter. The sun that drives nearly all life on the surface has no reach in the world below. The marine snow falls through this darkness. The deep currents move through it. The stratified water masses hold their positions in it. And the biological pump does its work invisibly without light, simply by the physics of density and gravity carrying organic particles down through a lightless world. The currents that move through this darkness are steered by the rotation of the Earth. The Coriolis effect, a consequence of living on a spinning planet, deflects moving water to the right in the northern hemisphere and to the left in the southern. In the deep ocean, this deflection shapes how the water masses flow once they have formed and sunk. The North Atlantic deep water, moving southward through the deep Atlantic, is pressed against the western edge of the basin by the Coriolis effect. It becomes what is called the deep western boundary current, a slow, deep river running along the western side of the Atlantic basin, carrying cold, dense water southward at depths of 2 to 4 kilometers, hugging the margins of the Americas as it goes. The Coriolis effect does not care that this water is in the dark. It steers the deep currents as impassively as it steers the storms visible from space. And so the water moves, not as a river moves, tumbling and quick over stone, not as the Gulf Stream moves, a warm, muscular current displacing itself at something close to 2 meters every second, enough to carry heat and color and warmth across hundreds of kilometers in a matter of weeks. The deep return flow moves the way glaciers move, the way continents move, by a patience that has no equivalent in ordinary experience. At centimeters per second, sometimes less. A single centimeter every second means 36 meters in an hour, less than a kilometer each day. In a year, such a current covers perhaps 300 kilometers, perhaps somewhat less. Compare that to the Gulf Stream, which can move its own length in minutes and cross the Atlantic in months, and you begin to understand that what lies below is not a slower version of the surface. It is something categorically different. It is the ocean working on a time scale that belongs not to weather or seasons or human lifespans, but to the deep history of the planet. This slowness is not a defect, it is the nature of the thing. The deep return flow creeps because it does not need to hurry. It has nowhere urgent to be. It sank off the coasts of Greenland or descended the Antarctic continental slope according to the same physics that governs a stone dropped in a pond, and now it drifts, heavy with cold and salt, through the absolute dark, following the gentle gradient of the ocean floor, turned by the slow insistence of the Coriolis effect, feeling its way along the deep basins of the world toward wherever the global architecture of water masses eventually allows it to rise. And it will rise. But first, it must travel. Consider what it means to follow a single parcel of that water. A specific volume of water, say a cubic meter, that tipped over the edge of buoyancy somewhere in the Nordic Seas in the Labrador Sea or down the Antarctic slope in the Weddell Sea and began its descent. The commonly cited figure for the circuit this parcel will eventually complete is roughly 1,000 years. Some estimates extend that to 2,000 years, depending on the path taken and the ocean basin in question. Neither estimate is easy to hold in the mind. 1,000 years ago, the Norman conquest of England had not yet happened. Notre Dame de Paris would not be begun for another century and a half. The civilizations that would produce the printing press, the telescope, the germ theory of disease, the understanding of plate tectonics, and the measurements that would eventually allow human beings to understand that this very parcel of water was down here moving in the dark, none of that had yet occurred. And that water has been down here since, moving, very slowly, on its way. The path it follows, in broad terms, goes like this. From its formation site in the high-latitude North Atlantic, the parcel flows southward along the deep Atlantic, pressed as we have seen against the western edge of the basin by the Coriolis effect, carried by the deep western boundary current. It passes beneath the equator, which has no visible presence in the deep ocean, no warmth that reaches this far down, no season that registers at 3 kilometers of depth. It continues into the South Atlantic, still cold, still dense, still carrying the chemical memory of the polar surface it last touched. Then it rounds the bottom of the world, entering the deep Southern Ocean, where it eventually joins the Antarctic circumpolar current, the mightiest continuous current on the planet, circling Antarctica without interruption because there is no continent to stop it, no land bridge to block its path. From here, the parcel may be carried eastward, redistributed, and eventually steered northward into the deep Indian Ocean, or carried further east and then north into the deep Pacific. This is a journey measured not in days or years, but in the slow accumulation of centuries. The North Pacific is where something remarkable can be observed, or rather inferred, because nobody watches a single cubic meter of water for 1,000 years. The deep water of the North Pacific is old, not in any metaphorical sense, but in a chemical, measurable, documentable sense. Water holds dissolved oxygen, and that oxygen is consumed over time by the slow metabolic processes of deep-sea life and by the oxidation of organic matter drifting down from above. The longer water has been out of contact with the atmosphere, the more of its oxygen has been consumed. Scientists can measure this. They can take a water sample from the deep North Pacific, measure its oxygen content and certain isotopic signatures, and infer from those measurements roughly how long it has been since that water last breathed the air. The answer for much of the deep North Pacific is something in the range of 1,000 years. Give or take, accounting for the complexities of mixing and the various pathways water can take, the deep water of the North Pacific Basin has not touched the surface since roughly the time when the medieval warm period was ending in Europe and the Mongol Empire was at its height. There is something almost unbearable about this in the best possible sense. The water in the deepest parts of the North Pacific, the water that has been down there in the cold and dark longer than most of what we call history, is not exotic or alien. It is made of the same molecules as rain. It once was at the surface, touching the sky, exchanging gases with the atmosphere, the way a slow sleeper exchanges breath with a room. Then it grew cold and heavy and it sank, and the world above it changed 1,000 times while it moved through its long underground, or rather underwater, detour. This water remembers, in a chemical sense, the atmosphere it last knew. And scientists, reading its oxygen, reading its salinity, reading its temperature against known baselines, can hear that memory. This is one of the quiet achievements of modern oceanography, that the deep ocean has been made partially legible. Water masses carry their signatures the way accents carry the trace of where a person grew up. The North Atlantic deep water, cool and relatively well oxygenated, still carries the stamp of its formation in the subpolar North Atlantic. The Antarctic bottom water, colder still and identifiable by its extreme density, carries the stamp of the Weddell Sea and the Ross Sea. These signatures persist for centuries because the deep ocean mixes only very slowly. A water mass formed in one place retains recognizable characteristics thousands of kilometers away and hundreds of years later. This is how oceanographers piece together the circulation without being able to watch it in real time. They read the water, they sample it, they measure it, they follow its fingerprints through the global abyss and reconstruct from those fingerprints a map of where the water has been and how long it has been traveling. And as the water travels, something is happening above it. Not visible to the water, of course, because the water in the deep is in a different world entirely from the surface, but happening nonetheless, and important, and connected to the journey below in ways that matter enormously. In the sunlit upper ocean, in the photic zone above those 200 meters of light, the photosynthesizing is never quite finished. There is always, somewhere in the world ocean, a bloom of phytoplankton beginning or peaking or ending. These are the smallest autotrophs, the microscopic marine plants. Though plants is a loose word for organisms that include diatoms, coccolithophores, cyanobacteria, and dozens of other groups, all of them absorbing carbon dioxide from the water around them and using sunlight to convert that carbon into organic matter. Carbon that was, in a meaningful sense, on its way into the atmosphere is instead being pulled into tiny living bodies floating in the sea. When those bodies die, or when the zooplankton that graze on them die, or when those grazers produce their fecal pellets, and this is perhaps the most important, unglamorous fact in all of ocean carbon science, that organic material begins to sink. The phytoplankton cell that fixed a carbon atom from seawater is now dead, drifting downward. The fecal pellet, compact and dense, sinks faster than the cell alone would, and as this material drifts past the photic zone, past the 200-meter boundary into the permanent dark, it is removed from the surface ocean, where gases exchange freely with the atmosphere, and enters the deep, where it may remain isolated for decades, centuries, or longer. This is the biological pump, not a mechanical device, of course, no moving parts, no engineers designed it, but a pump in the functional sense, moving carbon from where it could potentially re-enter the atmosphere to where it is, at least for a very long time, sequestered. And it operates continuously, driven by nothing other than the basic requirements of living things to eat sunlight, and the basic physics of gravity that pulls dead things toward the bottom. The scale of this process is not easy to visualize, which is perhaps why it does not receive the popular attention it deserves. Estimates suggest that the biological pump exports somewhere on the order of 5 to 10 gigatons of carbon per year from the surface ocean to the deep. A gigaton is a billion metric tons. 5 to 10 billion metric tons of carbon per year, falling as particles through the dark. These figures vary depending on the method of measurement and the assumptions built into models, and the scientific community continues to refine them, but even the lower estimates represent a quantity of carbon that would profoundly alter our atmosphere if it were suddenly released rather than stored. The biological pump is one reason the ocean holds so much more carbon than the air above it. The ocean, as a whole, holds roughly 50 times more carbon than the atmosphere. 50 times. The atmosphere that drives weather, that sustains terrestrial life, that we monitor and study and worry over, contains a small fraction of the carbon that the ocean holds. Most of that carbon is in the deep ocean, in the cold, dark water far below the surface, held there partly by the slow physics of density and circulation, and partly by the steady, invisible work of the biological pump. Without the pump, and without the deep circulation that keeps the ocean stratified and its deep water cool and dense, much of that carbon would return to the surface and eventually to the air. Atmospheric carbon dioxide would be substantially higher than it is. The climate of the planet would be substantially different. The particles that make up the biological pump's output are collectively called marine snow. It is a beautiful name for something that cannot be seen without powerful lights in the deep, but that exists everywhere, continuously, through all the world ocean. Not seasonal like snow on land, not occasional like a storm, constant. Every hour of every day, organic particles are drifting downward from the sunlit layer into the dark. If you descended through the deep ocean with a light, you would see them. Pale flecks, loose aggregates of organic material, diatom shells, fragments of zooplankton, fecal pellets, and the remains of things that once lived and caught sunlight, all drifting down like ash from a fire that has been burning for as long as there has been life in the ocean. The marine snow falls through the same water that the deep circulation is carrying on its long journey. The parcel of water we imagined sinking off Greenland 1,000 years ago is surrounded during all its centuries of travel by this silent downward drift. Carbon is arriving from above while the water itself moves laterally and very slowly northward or upward, depending on where in its circuit it finds itself. The two processes, horizontal deep circulation and vertical biological sinking, are not the same thing, but they are entangled. The deep circulation determines how long water stays in the dark interior, which determines how long the carbon carried there by marine snow can be kept from the atmosphere. A faster circulation would cycle water to the surface sooner, potentially releasing carbon. A slower or stronger stratification keeps water down longer, potentially sequestering carbon longer. The biology at the surface and the physics of the deep are in a relationship that spans the entire planet. Not all the marine snow reaches the bottom. Much of it is consumed or remineralized at various depths, decomposed by bacteria, and eaten by deep-sea organisms, the carbon partially returned to dissolved form in the water column. Only a fraction, typically a small fraction, actually settles on the seafloor as sediment, but even the dissolved carbon released at depth is, for the time being, out of contact with the atmosphere. It is in the deep water, circulating with that water, returning to the surface only when the deep water itself upwells, which is a matter of centuries. The people who formalized our understanding of how all of this connects, the surface, the deep, the carbon, the heat, did so over many decades, working with the limited tools of their time and eventually with an increasingly sophisticated array of instruments and models. Two names belong near the center of that history. Henry Stommel was an American oceanographer who did foundational work in the mid-20th century on the deep circulation and what happens to water masses once they sink. Stommel worked on the theoretical underpinnings of abyssal flow at a time when the deep ocean was largely unmeasured, when most of the instruments capable of following deep currents had not yet been built. He thought carefully about how the ocean must be organized if it is to circulate as observations suggested, how the thermohaline driving of sinking at high latitudes connects to the slow return flow, how the geometry of ocean basins and the Coriolis effect together produce the patterns of deep boundary currents. His work gave the field much of its conceptual vocabulary and many of its basic theoretical structures. Wallace Smith Broecker, working decades later, and with more observations available, was the person who gave the general public the image that has since become the standard way of picturing this system. In the late 1980s, Broecker popularized the phrase Great Ocean Conveyor Belt, and the simple schematic it brought to mind, a loop of water circling the planet, sinking in the North Atlantic, traveling deep, rising elsewhere, returning at the surface, made something genuinely complicated accessible in a way that scientific papers never quite manage. The phrase Great Ocean Conveyor Belt is a simplification, and Broecker himself understood that. The real system is more three-dimensional, more irregular, more branching and reconnecting than any single loop can suggest. But the image captured something true about the system's essential character, that it is global, that it connects all the oceans, that it involves sinking in one place and rising in another, and that it operates on a time scale vastly longer than anything visible in the surface weather of the sea. Broecker's contribution was not only the metaphor, he was also one of the scientists who drew serious attention to the possibility that the conveyor could weaken or change, and to what the climate consequences of such a change might be. This is a thread that runs through the science of the deep ocean with increasing urgency, and it is a thread we will come to in time. For the moment, it is enough to note that the name most associated with the popular understanding of the global circulation belonged to a man who also worried carefully and persistently about what happens when that circulation is disturbed. Monitoring the circulation in real time is extraordinarily difficult because the deep ocean is vast and the instruments of measurement are expensive and sparse. But since 2004, there has been a dedicated effort to keep watch on at least one critical stretch of the Atlantic meridional overturning circulation. This is the Rapid Array, a line of moored instruments deployed across the Atlantic at 26.5 degrees north latitude, roughly the latitude of the northern Bahamas cutting across to the west coast of Africa, measuring the strength of the overturning circulation on a continuous basis. The Rapid Array was the first sustained monitoring system of its kind, and the data it has produced since 2004 have given scientists a far more detailed picture of the circulation's variability than was previously possible. What the Rapid Array has shown is that the circulation is not steady. It fluctuates on timescales of days, seasons, and years. Some years it carries more water and heat northward, others somewhat less. This variability is not itself alarming, as the ocean has always had such fluctuations, but it provides a baseline against which longer-term changes can eventually be compared. And there are scientists who look at that baseline and at the broader evidence from the ocean and from climate models, and who carry a concern that the baseline itself may be shifting, that the overturning, measured at 26.5 degrees north since 2004, may be changing in ways that go beyond ordinary year-to-year variability. The evidence for this is debated, and the future trajectory of the circulation under a warming climate remains genuinely uncertain. What is not uncertain is that human beings now have instruments watching which they did not before, and that the watching itself is a form of respect for the system's importance. The parcel of water we have been following through the dark does not know any of this. It does not know the names Stommel or Broecker. It does not know about the Rapid Array transmitting its measurements upward through kilometers of water to satellite. It carries its oxygen, depleted over centuries by the slow consumption of the deep, and it carries its temperature close to zero or just below, and it carries its salinity, and it moves. And as it moves above it, far above, in the thin, bright skin of the ocean, where light still reaches and photosynthesis still runs, the marine snow continues to fall. Imagine if it helps to ground this in something sensory, descending through the ocean. At the surface, sunlight scattered and broken into shifting patterns on the water, warm, the oxygen of the atmosphere dissolving freely at the interface, plankton catching that light and building their bodies out of dissolved carbon. A busy world measured in hours and seasons, then down through the photic zone, light fading. At 100 meters it is dim. At 200 meters it is nearly gone. Below that, permanent dark. And in that dark, the snow is always falling, upward to you as you descend, so that you seem to be moving through a gentle, downward storm of pale particles, all of them on their way to the bottom, all of them carrying the trace of the sunlit world above. You pass through hundreds of meters of this, then 1,000, then 2,000. The temperature has long since settled into the range of 0 to 4 degrees Celsius. the remarkable uniformity of the deep ocean's cold. The pressure is enormous, but the water does not know pressure the way lungs do. It is essentially incompressible, and it carries that pressure as simply as it carries its salt. At 3 or 4 kilometers of depth, you are in the territory of the North Atlantic deep water. The water formed from the cooling and sinking of warm, salty surface water in the Nordic Seas and the Labrador Sea, flowing southward through the Atlantic on its long southward journey. The marine snow is still falling past you. The deep current is moving, imperceptibly by human standards, but measurably by the instruments that science has learned to build for exactly this purpose. And somewhere below you, deeper still, is the Antarctic Bottom Water, the coldest and densest layer, formed by the brine rejection that sea ice accomplishes at the margins of the Weddell Sea and the Ross Sea, settled at the very bottom because nothing in the ocean is denser than it. This is the world through which the parcel travels, cold, dark, slow, carbon arriving from above, deep currents carrying the water southward, and then over centuries working its way around the planet toward the places where it will finally rise. The deep water that entered the Pacific carries its age like a kind of patience. The North Pacific is, in the language of oceanographers, the oldest water in the global ocean in terms of time since last surface contact. It arrived there after the longest journey, after passing through the deep Atlantic and the Southern Ocean and the deep Indian Ocean, picking up its burden of consumed oxygen and its character of cold density, and it has been sitting in the deep North Pacific Basin, slowly upwelling or being mixed upward at rates even slower than the deep Atlantic flow for something approaching 1,000 years. In parts of the deep North Pacific, the oxygen content is measurably lower than in the deep Atlantic because it has simply been down there longer, and the slow processes of bacterial decomposition and deep-sea respiration have been at work for more centuries on those water molecules. This is the meaning of the deep ocean's layered architecture when viewed in time rather than space. The shallowest deep water is youngest, closest in chemical character to the atmosphere above. The deepest water, particularly the Antarctic Bottom Water, is the coldest and densest and was last at the surface most recently, in a sense, because the formation of Antarctic bottom water around Antarctica is an active, ongoing process. But the water in the deep North Pacific, the far end of the circuit, the place the water goes after traveling south and east and then north again, is the oldest, the most isolated, the most removed from the sky. It is the bottom of the circulation's timeline as much as it is the far end of its geography. And one day, in ocean time, meaning on timescales of centuries, the water will begin to feel the upward motion. Not all at once, not at a single moment or a single place. The return to the surface is not as dramatic as the sinking because there is no sharp density contrast driving a sudden descent. Instead, the deep water is lifted gradually, mixed upward by the mechanical stirring of winds and tides acting from above, carried toward the surface in regions where the deep water naturally rises. The most important of these regions, the great valve of the global system, is the Southern Ocean. Around Antarctica, the winds that circle the continent are the famously fierce westerlies of the Southern Ocean, unimpeded by land, drive surface water northward through a process that pulls deep water upward in its place. This is upwelling, and the Southern Ocean is the world's largest and most significant site of it. The deep water that has been circulating through the global abyss, the Antarctic Bottom Water, the North Atlantic deep water, the old deep water of the Pacific and Indian Oceans, eventually finds its way to the Southern Ocean, where it is lifted toward the surface, restored to the light, reoxygenated by contact with the atmosphere, given fresh nutrients that it has been accumulating in dissolved form during its long residence in the dark. Those nutrients, nitrates, phosphates, silicates, the raw materials of phytoplankton growth, are brought up from the deep in concentrations that make the Southern Ocean one of the most productive in the world, at least seasonally, when light permits. The parcel of water that sank off Greenland roughly 1,000 years ago is, in this long view, approaching its return. Not imminently, not quickly, but by the standards of the ocean, which has its own sense of time, the return is coming. The water will rise into the light. It will touch the atmosphere. It will exchange gases again, reoxygenating itself. Carbon dioxide from the atmosphere will dissolve into it. Carbon dioxide from its long, dark residence, the dissolved carbon accumulated during centuries of deep travel, may partly re-enter the atmosphere. And the water, restored and reoxygenated, will rejoin the surface circulation, warming at lower latitudes, moving northward along the surface, and eventually returning to the North Atlantic, where, if the conditions are right, and the cold is cold enough and the salt is salt enough, it will do the whole thing again. This is the closed loop. This is what makes the question of where the current begins and ends so difficult to answer simply, because it does not begin and it does not end. It turns. It has been turning in various configurations, but with this same essential character for as long as the continents have been arranged roughly as they are, which is to say, for millions of years. Individual water molecules have made this circuit thousands of times, though the word times feels almost too casual for a cycle that takes 1,000 years each lap. The water in the deep ocean right now is in the middle of a journey that started before any living person was born. The water that will sink in the North Atlantic this winter will not see daylight again until centuries from now. None of this is visible from the surface. The ocean, looked at from above on a calm day, gives no sign of any of it. The surface is blue and bright, and the waves move at their ordinary human pace, and the birds wheel above it, and the ships cross it. The deep is entirely hidden, and yet the deep is what the surface runs on. The entire circulation, so the surface currents and the deep return flow together, is one system, and the surface cannot be fully understood without the deep, and the deep is sustained by what the surface gives up, its heat, its salt, its sinking water. The connection between the surface and the deep is not only a matter of temperature and salt, it is also a matter of time. The surface lives on timescales of days and seasons. The deep lives on timescales of centuries and millennia. When scientists want to understand how the climate has varied over thousands of years, what the ocean was doing during the ice ages, how the circulation shifted in the past, they turn to the deep ocean's memory. The sediment that has accumulated on the ocean floor over geological time carries the chemical record of what happened at the surface above it, delivered down through the water column by the very marine snow that is falling today. Ice cores from Greenland and Antarctica carry the record of the atmosphere at the time the ice formed. Deep sea cores carry the record of water temperature, species composition, and carbon fluxes over hundreds of thousands of years. The slow systems preserve what the fast systems forget. The biological pump, the marine snow, the thermohaline circulation. These are systems that have been operating long before human beings existed to notice them, and they will, in some form, continue after. But they are not unchanging systems. They have changed in the past, sometimes abruptly, sometimes drastically, in ways that left their mark on climate and on the history of life. And they are changing now, or maybe, in ways that are not yet fully understood. The monitoring work, the rapid array at 26.5 degrees north, the Argo float program that samples the ocean's temperature and salinity profiles across the globe, the satellites that measure sea surface temperature and color and height, is the closest thing humanity has to a nervous system laid over the ocean. It tells us, in something approaching real time, what the ocean is doing and whether it matches what models predict, and whether past patterns are holding or shifting. it is not enough. The ocean is vast and the instruments are sparse, and the data are hard-won, but it is far more than was known 50 years ago, and it is continuing to grow. Broecker, who spent his career thinking about the ocean's circulation and its consequences, understood something that the instruments are now beginning to confirm in detail, that the conveyor is not a passive feature of the planet, not a permanent fixture like a mountain range. It is a dynamic system sustained by ongoing physical conditions, a certain balance of temperature and salinity, a certain pattern of winds and heat exchange, a certain flow of fresh water from ice and rivers, and when those conditions shift, the system can shift with them. The magnitude and pace of possible change is what is debated and uncertain, but the possibility of change is not. For now, the water moves, the marine snow falls, the deep currents creep through the dark at centimeters per second, patient beyond any human analogy. The North Pacific holds its ancient, oxygen-depleted water. The Weddell Sea sends fresh pulses of Antarctic bottom water down the continental slope. The rapid array measures the strength of the overturning at 26.5 degrees north and sends its data toward the surface and the sky. And somewhere in the deep, a parcel of water that sank off Greenland or in the Labrador Sea is moving southward through the dark, surrounded by falling marine snow, carrying the chemical memory of the surface it left behind, beginning the long circuit that will bring it eventually to the Southern Ocean and the light. And that parcel of water moving southward through the dark is not traveling empty. It carries something we have not yet fully accounted for, something that makes the conveyor more than a river of water through the sea. It carries heat. The Atlantic meridional overturning circulation moves warmth northward on a scale that has no human equivalent. The number attached to this is almost too large to sit with comfortably. Roughly 1.3 petawatts of heat, 1.3 times 10 to the 15th watts, flow northward through the North Atlantic aboard this current. A petawatt is 1,000,000 gigawatts. A single, large modern power station produces about 1 gigawatt of electricity. To match what the Atlantic conveys northward as heat, you would need something close to 1,000,000 such power stations, all running continuously, all pointed north. And yet there is no machinery, no fuel is burned, no turbines turn. The heat moves because the water itself moves, and the water moves because of cold and salt. That heat does not stay in the ocean. As the current travels north and the water above it, the surface expression, the Gulf Stream and its northern extension, the North Atlantic current, pushes toward higher latitudes. The warmth it carries meets the cold polar air. The ocean gives its heat to the atmosphere. The exchange happens quietly, invisibly, over millions of square kilometers of open water between roughly the middle latitudes and the Norwegian coast. The atmosphere absorbs it. The winds carry it east and then farther east toward the land, and the land feels it. Northwest Europe sits at latitudes where, by rights, the climate should be far more severe than it is. London lies at about 51 degrees north. That is the same latitude, roughly, as the coast of Labrador in Canada, or the southern tip of Newfoundland. Those Canadian regions are cold. Labrador endures winters that would strike most Europeans as genuinely extreme, temperatures falling well below freezing for months, sea ice forming along the coast, a landscape that spends much of the year under snow. London does not. London has mild winters, rain, fog, occasional frost, but nothing like the cold that its latitude on its own would predict. The British Isles sit in the path of the ocean's generosity and are warmed by it. Paris, Amsterdam, Copenhagen, Oslo, all of them benefit from the same transfer. The ocean's heat is in the air that reaches them. This is the standard story, and it is true as far as it goes. But it is worth pausing here because the full picture is more complicated than the simplified version suggests, and the simplified version has been repeated so often and so confidently that it has come to carry an authority it only partly deserves. The common telling runs like this: the Gulf Stream keeps Europe warm. Without the conveyor, Europe would freeze. This is the frame that a 2004 film dramatized in spectacular and completely fictional fashion. A story in which the Atlantic circulation shuts down over a matter of hours, and the Northern Hemisphere is plunged into a new ice age within days. That film was entertainment, not science. Any genuine change in the circulation, even a significant one, would unfold over years and decades, not overnight. The ice does not come in a week. But the film fixed something in the popular imagination, and the simpler version of the story, the Gulf Stream as Europe's sole heating system, has been stated so frequently in so many places that it has taken on the quality of established fact. Researchers have pushed back on this. Work published in 2002 by Richard Seeger and colleagues argued carefully that the ocean current, while genuinely important, is not the only reason Europe enjoys mild winters. The analysis pointed to other factors that share the credit. Prevailing westerly winds blowing in from the Atlantic carry warmth inland across the continent. Those winds blow over an ocean that is itself warm, and they pick up that warmth and deliver it to the land. The atmosphere is an active participant in the redistribution, not merely a passive recipient of what the ocean provides. And there is the matter of what the ocean does seasonally. The sea absorbs heat during summer and releases it slowly through winter, acting as a thermal buffer, moderating the extremes that a purely continental climate would otherwise produce. Together, these effects, the westerly winds over a warm ocean surface, the seasonal release of stored warmth, and the contribution of the overturning circulation itself, combine to produce the mild European climate that generations have taken for granted. The honest version, then, is this. The Atlantic circulation contributes significantly to the relative warmth of northwest Europe, and the 1.3 petawatts it carries northward are a real and consequential part of the planetary heat budget. But the current is one contributor among several. The atmosphere does its own work. The seasonal memory of the ocean's surface does its own work. To say the Gulf Stream alone keeps Europe warm is to give the ocean sole credit for something that is, in fact, a collaboration between water and air and season. The simplified version is not wrong in the way that a fabrication is wrong. It is wrong in the way that a partial truth told too confidently becomes a misleading one. That distinction matters because the consequences of getting it wrong cut in two directions. If the conveyor carries all the credit for European warmth, then any weakening becomes catastrophic by definition. If the conveyor is one important contributor among several, then its weakening is serious, possibly deeply serious. But the picture is more nuanced and the response more calibrated. Science prefers calibration. And there is reason to think about what a weakening would mean, because the circulation has not always been as it is tonight. The past holds warnings written in sediment and ice, in the isotopic ratios of ancient shells and the chemical layers of Greenland's long ice cores. The record is there, and it is not entirely reassuring. Roughly 12,900 years ago, geologically recent, in the deep chronology of the Earth, though ancient beyond easy imagining in human terms, the planet was emerging from the last glacial maximum. The great ice sheets that had covered much of North America and northern Europe were retreating. The climate was warming. And then something interrupted the warming with abrupt and dramatic speed. Within decades, possibly within years, temperatures in the North Atlantic region plunged. The warming stalled, the cold returned. This episode is called the Younger Dryas, named for a small Arctic wildflower, Dryas octopetala, whose pollen appears in European sediments during that frigid interval, far south of where it grows today. The Younger Dryas lasted approximately 1,000 years, and the hypothesis that has gathered the most evidence, though it remains debated in its fine details, is that it was triggered by fresh water. As the ice sheets melted, vast quantities of meltwater, fresh, light, low salinity, flooded into the North Atlantic. This sudden pulse of fresh water is hypothesized to have diluted the surface waters enough that they could no longer grow dense enough to sink. The salinity dropped, the sinking slowed or stopped, the overturning circulation that had been carrying heat northward was disrupted. The ocean's heat delivery to the North Atlantic region was interrupted, and the cold followed. It is a reminder written in the past. The sinking that drives the conveyor depends on salinity, and salinity can be changed by what arrives at the surface. Fresh water arriving too fast, from melting ice, from altered precipitation patterns, from rivers draining changed landscapes, can freshen the surface ocean enough to reduce or prevent the sinking. The mechanism that drives the entire global loop is sensitive to the balance it requires, and that balance has been disturbed before. Scientists monitoring the modern Atlantic have not been entirely reassured by what they measure. The rapid array, operating at 26.5 degrees north and sending data back since 2004, provides the most continuous record yet of the AMOG strength. The data show variability. The circulation is not steady, it pulses and fluctuates on timescales of days to years. And some analyses of those measurements and of longer proxy records reaching further into the past suggest that the modern circulation may be weaker than it was in previous centuries. Whether this represents a significant trend and what it portends remains actively debated among scientists. Precise predictions of future behavior are genuinely uncertain. The science is honest about that uncertainty. Weakening is documented in the record, the pace and magnitude of future change is not. What can be said is this: the circulation is sensitive and the sensitivity is real, and the past demonstrates that abrupt change is not only possible but has happened. The Younger Dryas is not a theoretical exercise. It is an event in the ice cores, preserved for anyone patient enough to look. It happened. And what caused it was not gradual, it was a threshold crossed, a balance upset, a system that shifted from one state to another. The film version of that shift takes hours and produces walls of frozen water rising over Manhattan. The real version took decades at most, possibly less, and produced 1,000 years of cold. By human standards, that is still staggering. By the planet's standards, it is quick. The deep ocean works on geological time, and even it can be startled into change. But tonight, the system holds. Tonight, the sinking proceeds in the Nordic Seas and in the Weddell Sea. Tonight, the heat moves northward, and the carbon falls downward, and the deep water creeps southward through the dark. And the final chapter of our drops-long journey is approaching. It has been traveling for a very long time. Imagine following it, though imagination is the only instrument available for this particular observation, since no human eye has ever watched a single parcel of water complete the full circuit. It sank in the way we have described somewhere in the North Atlantic. It carried its heat to the polar air and gave it away. It grew cold and dense. It sank below the lighter water around it. It joined the deep western boundary current and turned southward, following the western edge of the ocean basin, steered there by the Coriolis effect of the turning Earth. It traveled south through the Atlantic at the pace of centimeters per second, a pace so slow that if you marked a drop of water and watched it, you would see nothing moving. You would have to wait months to see it cross a room. It moved south past the latitude of Bermuda, past the latitude of the Caribbean, past the equator into the South Atlantic, carrying its chemical signature, its temperature, its salinity, its age, as recorded in the slow consumption of its oxygen by deep-sea organisms, toward Antarctica. Along the way, it was joined by other deep water, other parcels that had sunk from other surfaces at other times, mixing slowly at the boundaries between water masses, the stratified architecture of the abyss, blending at its edges though remaining distinct at its core. It reached the waters near Antarctica. It encountered the Antarctic Bottom Water, that coldest, saltiest, densest water on Earth, born in the Weddell Sea and the Ross Sea by the expulsion of salt from freezing sea ice. And that bottom water moved beneath it, claiming the absolute floor of the ocean as its own. Our parcel, North Atlantic deep water, rode above the Antarctic bottom water, denser than the ocean above, but not as dense as the water below. The stacking of the abyss, organized by density, accommodated it. And then the system began very slowly to lift it. The Southern Ocean is the mixing valve of the whole global loop. It is here, in the waters that circle Antarctica with no continental barrier to interrupt them, that the circulation closes. Winds over the Southern Ocean, the westerlies that blow around the high southern latitudes with a strength and persistence matched nowhere else on Earth, drive a massive upwelling. They push the surface water northward, and to replace what leaves, deep water rises from below. It is not a gentle or localized process. The Southern Ocean upwelling is one of the largest and most important upwellings in the global ocean, lifting water from depth across an enormous area, returning to the surface the water that sank, sometimes 1,000 years before. Our parcel, creeping southward and then rising toward the Antarctic surface, is approaching the end of a circuit that began with a moment of density, a moment when cold and salt conspired to make it heavier than the water around it and send it down. And now, at the other end of the loop, wind and geometry conspire to bring it back up. It has crossed the Atlantic twice, south at depth, back at the surface. It has been carried around Antarctica. Its journey has taken it through the Indian Ocean and contributed, in some fraction of its mass, to the deep water that rises off the coasts of places it has never been close to. It has traveled something on the order of tens of thousands of kilometers. 1,000 years have passed. When it reaches the surface of the Southern Ocean, or rather, when the fraction of its atoms that carry this story upwells into the sunlit layer, it meets the atmosphere again for the first time since the North Atlantic. The gases it carries are stale. The oxygen it held when it sank has been partially consumed by the deep sea life it passed on its journey, the bacteria and the small organisms of the abyssal dark that rely on what falls to them from above. It surfaces with a kind of chemical exhaustion, carrying less oxygen than it held when it sank, carrying more of the dissolved inorganic carbon produced by respiration in the deep, carrying the accumulated record of a millennium of travel. But the surface ocean is alive. Light penetrates the water. Phytoplankton grow. The water gives up its carbon dioxide to the atmosphere in exchange for oxygen. It warms. The salinity that helped sink it is diluted by rain and snowmelt and the freshwater contributions of the polar environment. And it begins gradually to lose its identity as deep water, to become surface water again, to enter the surface circulation, to be pushed by wind and heated by sun, to travel northward, perhaps into the Pacific, perhaps eventually back toward the Atlantic by the long southern route, perhaps toward the Indian Ocean. The 5 oceans, all the while, have been behaving as one. The Atlantic and the Pacific and the Indian and the Southern and the Arctic are the names we give to the one connected ocean that covers more than 70% of the planet's surface. The thermohaline circulation, the global conveyor, stitches them together into a single system with a single loop. Water that sank off Greenland has traveled through all of them. A drop rising now in the Southern Ocean may, in another 1,000 years, be sinking again in a northern sea, carrying the memory of the surface it touched today. The loop closes, and then it opens again, This is the answer to the question the title asks. Where does the ocean's global current begin and where does it end? It begins in a handful of small places near the poles. The Nordic Seas, the Labrador Sea, the Weddell Sea, the Ross Sea. Wherever cold air and salty water conspire to create something denser than what surrounds it. It begins every time a parcel of water grows heavy enough to sink. It begins in the moment that brine rejection leaves behind a drop of water so cold and so salt-laden that the only direction available to it is down, and it ends. But it does not end. It is a closed loop, and closed loops have no ending, only returns. What ends is the particular journey of a particular parcel. When that water surfaces again, when it re-enters the sunlit world, when it breathes the atmosphere and releases what it carried and takes up something new. That surface, that breath, is as close to an ending as the circulation allows. And then the conditions may be met again, the cooling, the sinking, and the circuit begins once more. What the loop accomplishes in its passage is what makes it worth 1,000 years of attention. It moves heat, it moves carbon, it moves oxygen, it moves the nutrients that deep water accumulates during its long, dark transit, and delivers them at upwelling back to the photic zone where light can use them. The upwelling Southern Ocean is among the most biologically productive regions on Earth, and that productivity is fed by what the deep circulation returns from below. The phytoplankton that grow in those nutrient-rich waters photosynthesize, absorbing carbon dioxide. Some of them die and sink as marine snow, and the biological pump begins its quiet work again, pulling carbon out of the surface and sending it back into the abyss. The loop within the loop, carbon descending while deep water descends, carbon ascending as deep water ascends, the whole system cycling material through the planet's largest reservoir of dissolved carbon, keeping far more of it in the ocean than the atmosphere would otherwise hold. The ocean holds roughly 50 times the carbon contained in the atmosphere, not 50% more, 50 times as much. The atmosphere you breathe, with its carefully balanced carbon dioxide concentration that makes the greenhouse effect tolerable and life as we know it possible, represents a small fraction of the carbon the ocean keeps. The deep ocean is where most of it resides, held there by temperature and chemistry, and the biological pump's continuous work, kept from the air by the sheer depth and slow circulation of the abyssal world. If that carbon were released, if the deep ocean were somehow stirred and mixed rapidly with the surface, the consequences for the atmosphere would be enormous. The ocean's vast, cold, slow interior is not a passive storage tank. It is an active regulator of the carbon that determines the climate above it. And the regulator runs on cold and salt. That is the fundamental simplicity at the heart of all of this. Temperature and salinity set density. Density decides what sinks and what floats. What sinks pulls the rest of the system into motion. The loop runs because cold, dense water seeks the bottom, and warm, light water rises to fill the space it leaves, and the planet turns, and the winds blow, and the phytoplankton grow, and the marine snow falls, and the cycle continues, as it has continued, in some form, for as long as the ocean has been here. Wallace Smith Broecker, who spent decades thinking about this system and named it in the terms that entered public consciousness, understood it as something fragile in its elegance. A machine made not of metal, but of physics, sustained not by any external power source, but by the ongoing differences between one place and another on the surface of the same planet. The Nordic Seas are cold and the tropics are warm, and that difference is enough to drive a circulation that spans the entire world ocean. The Atlantic is saltier than the Pacific, and that difference is enough to determine where the circulation sinks and where it does not. Small differences sustained over large areas add up to forces that dwarf anything humanity has built. and small changes in those differences, a freshening here, a warming there, can alter what the differences sustain. Henry Stommel understood it earlier still in the theoretical foundations laid in the mid-20th century when the abyssal circulation was more concept than confirmed measurement. He worked out the mathematics of what density-driven flow should look like in a rotating ocean, and the deep western boundary currents he predicted were eventually found where he said they should be. The theory preceded the observation, and the observation confirmed the theory. This is science doing what science does, slowly and with difficulty, and in the end arriving somewhere real. The rapid array at 26.5 degrees north continues its vigil. The instruments measuring the strength of the Atlantic overturning send their data upward through the water column, and those data accumulate year by year into a record that is longer and more detailed than anything we had before, even though it is still short by the standards of the system it monitors. A decade or two of continuous measurement against a system that operates on thousand-year timescales is a narrow window. But the window is open and the view is growing clearer. And what those instruments measure, what the ice cores record, what the sediments preserve, is a system in motion, not static, not permanent, but the product of conditions that can change. The Younger Dryas happened. The fresh water that disrupted the sinking came from melting ice, and the ice melted because the world was warming from a glacial maximum, and the warming was part of a natural cycle driven by the Earth's orbital geometry. The disruption was natural. The recovery was natural. The 1,000 years of cold and the gradual return of the circulation were natural. The planet has done this before without any help. The current world is warming again from different causes, not the orbital rhythms of the Milankovitch cycles, but the accumulation of greenhouse gases in the atmosphere. And the ice is again melting and fresh water is again entering the North Atlantic from Greenland's diminishing ice sheet and from changed precipitation patterns. Whether the quantities are sufficient to significantly alter the salinity of the North Atlantic surface, and whether that alteration is sufficient to reduce the sinking enough to slow the overturning, and at what pace and to what extent, these questions are genuinely open. The rapid data suggest variability. The proxy records suggest the system has been stronger in the past. The physics suggests sensitivity. The magnitude and timing of what happens next is where the uncertainty lives, and it is real uncertainty, not manufactured doubt. What is not uncertain is the mechanism. The mechanism is cold and salt. The mechanism is density. The mechanism is the simple fact that heavy water sinks and the void it leaves must be filled. This has been true for as long as the ocean has existed. It will be true for as long as the temperature differences between the equator and the poles persist, and the salinity differences between the Atlantic and the Pacific persist, and the sea continues to freeze around Antarctica in winter. The mechanism is as old as the planet's oceans and as immediate as tonight. Tonight, the water is moving. Somewhere in the Greenland Sea, a surface parcel is cooling in the long polar dark, losing its last degrees of warmth to the air above it, approaching the density at which it will slip below the water around it and begin the long descent. The sinking, quiet and invisible to any eye above the surface, is happening right now. 1,000 meters below the Weddell Sea, Antarctic Bottom Water completed its descent hours or days ago and is moving northward along the ocean floor, the coldest and densest layer of the world ocean, creeping at a pace that makes glaciers seem hasty. Somewhere between those two things, behind the sinking and the crawl, is the marine snow. It is always falling. Right now, at every longitude and in the darkness below every ocean on Earth, the fine particles of organic matter are drifting downward. Dead phytoplankton, fragments of the creatures that ate them, the fecal pellets of copepods and krill that grazed at the surface and sank their waste into the dark, the remains of things that never had names and never will, all of it falling, all of it carrying carbon toward a depth where it will be held for centuries, removed from the sky, tucked into the cold dark as quietly as snow settling on a field at night. And somewhere in the Southern Ocean, the upwelling is occurring. Deep water, water that has traveled from the North Atlantic, from the floor of the abyss, from beneath the ice of Antarctica, is rising. It is returning to the light. The nutrients it carried, accumulated over a century or a millennium of deep transit, are approaching the photic zone. The phytoplankton are waiting, or will be waiting, when the season turns and the light returns. The biological pump is preparing for another cycle. This is the whole system held in a single breath. It is a system whose scale is difficult to fully apprehend and whose simplicity, once grasped, is almost startling. No engine, no pump, just the planet tilted at its axis, warmed unevenly by the sun it orbits, its oceans made of water whose density is set by temperature and salt, and the relentless action of gravity pulling dense water down and lighter water up to fill its place. The global conveyor belt runs on the difference between a warm equator and cold poles, and on the fact that the Atlantic is saltier than the Pacific, and on the fact that sea ice, when it freezes, leaves its salt behind. From those simple facts, everything follows. The heat that reaches London in the winter air, the carbon that stays in the deep and out of the sky, the oxygen that deep-sea creatures consume in the dark, the nutrients that rise with the Southern Ocean, upwelling to feed the blooms of phytoplankton that will in turn begin the cycle of marine snow once more. All of it is downstream from cold and salt. All of it follows from density. The drop that sank off Greenland 1,000 years ago has now risen somewhere near Antarctica. It is at the surface. It is breathing the sky. It is warm, relatively speaking, compared to the deep it came from. Though the Southern Ocean is cold by most standards, it has discharged its cargo of accumulated carbon and taken up fresh oxygen. It has been remade, more or less, into something the surface world can use again. And the conditions of cold and salt that might eventually send it down again are not far off in the long calendar of the ocean. This is not a story with an ending. It is a story in the shape of a circle, and circles return to where they began. The water goes down and comes back up. The carbon goes down and much later comes back up. The heat that warms the North Atlantic is taken from the surface water that will, upon cooling, sink and return the favor to the deep. Everything is in transit. Everything is connected. The 5 oceans are one ocean, and the one ocean is the planet's great regulator of heat and carbon and oxygen, and it runs on a mechanism so simple and so ancient that it was here long before there was anyone to notice it. But someone has noticed it now, the oceanographers who built the rapid array and read its data, the researchers who drilled the sediment cores and read the chemistry of ancient shells, the scientists who carried Stommel's theoretical equations forward into the field and found the deep western boundary current where he said it would be. The careful work of generations, patient and cumulative, has given us a picture of something that cannot be seen directly, the abyssal circulation of the world ocean. And the picture, incomplete as it remains, is real and specific and grounded in evidence. It is one of the quieter achievements of modern science to have found in the cold dark below the sea a river that a single drop of water takes 1,000 years to complete, and to understand, at least in outline, why it flows. There is something in that, in the 1,000-year loop, in the drop that sinks in one millennium and rises in another, in the carbon that falls through the marine snow to rest in the abyss for centuries. That is, if you allow yourself to feel it, rather than only think it, genuinely calming. The world is very large and very old and very slow in the ways that matter most. The ocean has been circulating since long before any of us arrived, and it will be circulating long after. The processes that govern it are simple and physical and do not require any witness. They proceed in the dark at centimeters per second with a patience that makes the word patience feel inadequate. You can set down the speed of the surface world for a moment and let the ocean's timescale sit with you. 1,000 years, one circuit. The water moves, and the carbon falls, and the heat travels north, and the drop returns. And somewhere in the Greenland Sea, even now, a parcel of water is cooling. It is growing dense. It is about to sink, and the whole long journey begins again. If you have followed this to here, through the sinking and the deep and the marine snow and the heat and the upwelling and the return, then you have traveled something of the distance the water travels in the only way available to a person above the surface. It is not a small distance in understanding, and there is nowhere else to go to find this out, no competitor for the drop's attention, no other route through the abyss. The circulation goes where it goes, and it takes what it takes with it. And this is what it is. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know whether you are somewhere near the North Atlantic, whose mild winters owe something to the current we have been following, or somewhere far from any ocean, or somewhere that the Southern Ocean upwelling has touched in ways invisible to daily life. The comments are there, and I read them, and the geography of who listens to the slow stories is something I think about. There are more stories here, of the same slow and careful kind, waiting for whenever you want them. The world is full of systems that have been running quietly longer than anyone has been around to ask why. This has been one of them. You have done enough for one night. Let the water move where it moves. Let the marine snow fall. Let the deep be dark and cold and patient and vast. Like the old Stoics, let the day go. Tomorrow can be tomorrow's. Good night. Sleep well.